Hello and welcome to another edition of the EWI Technology Podcast. I am here in wonderful Columbus, Ohio at the EWI Center, and today we are going through a number of fantastic interviews where we are learning lots about some really great scientific R&D that's happening here at EWI. Today, right now, I have Jeff Ellis, who is the Senior Technology Leader for Polymers. Is that correct?
That's correct.
All right, Jeff, how are you doing today?
I'm well. How are you?
I'm doing good, and it feels like Canada outside. There's snow coming down. There's ice on the streets. I was right at home.
Yeah, it's a cold one this morning. My kids were excited for the dusting of snow this morning. Got to walk to school in it.
Yeah, I came from Saskatchewan, so we have about 2 feet of snow right now.
Okay.
So like I was saying to Matt this morning, I was like, yeah, this is kind of a little taste of home. It made me feel good.
Yeah. Hope you brought your jacket.
I did. I was ready. Although my luggage didn't show up till this morning because it got lost on an airplane. But
always fun.
That's flying.
Right.
All right, Jeff. So, here at EWI, there's always a number of research projects going on for a number of really interesting clients. But one of the things that kind of gets lost in the MJATS world, which is like the materials and joinings world, is the polymers and the plastics and all these new components that are coming up. I think most people historically, when they think of welding or of joining, and the sciences behind it, they're thinking of metals. But as we know, the future will require a whole host of other materials to be in the game in order to meet our supply and demand of what we need and the chemicals that are going to be being produced. What is it that you do, or what does your team focus on here in terms of polymers, and explain a little bit what your job is?
Yeah, sure. So we are Polymers Group. We do a lot of plastics. We do thermosets. We do thermoplastics, so things that can be remelted, recycled. And we also work on joining technologies for polymers to other materials, so we can make composites out of them. So if you think about your airplanes now that are made out of thermo set composites a lot of times to make them lighter, make them more fuel efficient. Those are things that we're working on, and joining those to, say, the aluminum ribs underneath. So joining the skin to the aluminum. We're working on laser techniques to join composites together. We're working on polymer to metal joining that gives really good strength without an adhesive. So quite a few different opportunities in the market. Another example might be automotive interiors. Used to have more real materials, I'll call them, more wood,
Leathers,
leather.
Yeah.
Now all of those are polymer materials that are like wood or are like leather. So we can actually do joining on those, and those would be dissimilar materials coming together, say at the edge of the seat or on the dashboard where you have multiple materials. Those still need to be joined. They could be joined with adhesives, but we're coming up with ways to do it without adhesives that makes them more environmentally friendly. It makes them more easy to separate at end of life, so they're more recyclable.
Okay, right.
So we're trying to be green about the technologies that we're kind of adapting into the future.
Yeah. Now, when we were talking earlier, right prior to the show, you said there's kind of two heads to this beast. One is sort of the joining side, and one, you said it was the degradation side. And you said you kind of work specifically on the degradation side of that process. So what is the degradation side of polymers?
Yeah, so I guess to expand on that a little bit, I can work on all parts of product development, anywhere from innovation of new designs, new products, to a lot of material selection, but choosing the right material for what we're doing. And in doing that, in choosing the right material, we have to worry about those kind of degradation rates and how the modes of degradation, how it's going to function in service in the future. So that's where I get into, when I'm choosing a new material, we need to understand how it's going to degrade later, and is it going to last the lifetime of the product in its intended service life?
Right.
So we do quite a bit of accelerated aging on materials to do that. That includes putting polymers under many different types of environments. So things like putting them in ozone to create oxidation.
Yeah.
Putting them in a UV cabinet, so getting basically artificial sunlight put on them.
And UV is a big issue for polymers, if I understand. Yeah.
Yeah, if they're outside, either you have to worry about the chemical package that's in the polymer so it can accept those free radicals that occur and squelch them, or we need to worry about getting it out of the UV.
Yeah.
Right. So we can simulate that here with our QUV cabinet that has 340 nanometer peak light bulbs in it that mimic Arizona sunlight at noon.
Right.
We can quickly put a lot of...
A nice tanning bed.
It is. If you left it open and stood next to it, you would get burned. So
Yeah.
a lot of safety precautions around that.
Yeah.
We make sure we don't do that. So those are ways we do oxidation. We can do hydrolysis, which is another way that polymers fail in the field. So if it's hot and humid, then you can start to get hydrolysis. You get chain scission. You get breakdown of that polymer. It becomes brittle. It cracks. So we're able to accelerate those as well. And then we do a lot of creep and stress relaxation testing, where say you have a part that has maybe a constant force on it, like a spring. So if you think of like a metal or a medical auto injector
Okay. Yeah.
with a large spring in it because it has to push the fluid through a small needle, there's constant force on all the plastic parts that are around that spring. So we have to worry about how much those creep while it's on the shelf before the user uses it, so it works every time. And we can do that in a short amount of time using our dynamic mechanical analysis. And we can do about a week's worth of testing, and then we can use time temperature superposition modeling to tell you what it's going to do 5 years from now.
Okay. Now, all these terms you're talking about, when people think of EWI, the Edison Welding Institute, they automatically have these thoughts about steels and alloys. But the terminology you're using when you're talking about plastics and polymers is pretty much the same terminology that we use in the steel industry. Is it very much the same kind of, issues and obstacles that you encounter when it comes to, both joining, wear, and lifespan?
So I think those are similar obstacles,
Yeah.
but the material science behind them is very different.
So you're not talking crystals, you're not talking lattices.
There is some of that in polymers,
Okay.
but the kind of time scale is different. It's
Okay.
it's very much faster in metals because we're talking about electrons moving around. I'm talking about polymer chain mobility. It's much slower diffusion.
Okay.
We have to worry about things moving on a longer period of time and moving farther. So the yield strain on a polymer might be 6%.
Oh, wow.
And a metal, you're usually not going to see that unless it's some crazy alloy.
Yeah.
So some of the ideas are the same. The idea of choosing the right material for the right part, for the right
Product.
and environment is still all there.
Yeah.
But again, the material science background is on a molecular level or atomic level. It's completely different.
Now, when you're looking at the modern technology that's coming out and the new, I guess, expectations of the materials we need to move back and forth, we're looking at, oils, we're looking at hydrogen, we're looking at CO2, we're looking at all these things. Are polymers going to be important or a leader in that industry? Because I know there's so much investment and time being spent into, how do we refurbish these old aging steel pipelines to do this work? Then the conversation comes, well, maybe we just need to put new pipelines down. Are these in the polymer world? Is this what we're looking at?
No, this is a great question. Polymer composite pipes. I'm working on an 18-month literature review for the federal government right now and have a workshop tomorrow on it. So this is a good question to go for. And the composite pipes that are out there, they're multi-layer. They have usually high-density polyethylene inner liners, and then they have a reinforcing layer around that, and then they have another polymer layer to protect the reinforcement layer from the environment. And those pipes can go maybe up to 3,000 psi.
Oh, wow.
So not as high as a steel pipe can.
Yeah.
But that inner layer, being the polyethylene, is very chemically resistant.
Yeah.
So it's it doesn't corrode like a steel pipe does. So it is great for use for hydrogen and for CO2. The thing that we need to look for the most is permeation. So polymers are kind of like a screen door. There's
Yeah.
always going to be some gas going through your polymer, unlike a steel.
They're not going to be like a steel where it's a hard stop, right?
Right. So
Yeah.
we just have to understand that rate of permeation at different temperature and pressures so we know how much is going through and we can manage it. But in terms of lifetime of the pipe, really, it should be longer than a steel pipe that could possibly have hydrogen embrittlement or
Yeah.
hydrogen-induced corrosion.
And what about issues like, like eddy, like the eddy resistance of joints and stuff like that? Is that also an issue with polymers? Like any type of disruption in the liner will cause like a weak spot? Because I know that's such a big issue with steel, and especially with the welding of steel.
That's still an issue. So we could get erosion in the pipe. So the inner liner could erode. We could get, if we get eddy currents, we could get spots that are a little bit thinner. The good news about the composite pipes that are coming out now, most of the reinforcement or most of the strength, the hoop strength, is from the reinforcement, not from the inner liner.
Right.
So if you make that inner liner thick enough that it's going to last the lifetime of the pipe, the strength will still be there, because of that reinforcement.
And is it more flexible? Like, people think of plastic as more flexible, but I know because there's plastics now that are stronger than steel. So when you're looking at the polymers you're working at, are these fairly flexible?
So these pipes are actually spoolable.
Wow.
So they extrude them as a single pipe. You can get 1,000 to 2,000 meters on a spool.
Wow.
So you don't need to weld every 40 feet like you do with a steel pipeline. So there's installation costs that are much less. And really safety issues that are less because you're not welding every 40 feet. So you do have to worry about connectors. So getting the connectors on there properly, making sure there's not strain concentrator right at the edge of it, making sure that it's going to be made of metal, so it doesn't have hydrogen issues or CO2 corrosion issues. But in general, the major part of the pipeline, for an 8-inch pipe at least, we can do a couple thousand meters before
having to worry about that. Yeah.
Right. You just lay it down. And you can also, your other question was, can we look into kind of refurbing the old pipelines that are out there? And a lot of these pipes you can pull through. So they're smaller than the steel pipeline. So we can actually use them as a liner, and we can pull them through the old pipeline. So we lose some of the diameter, some of that volume.
But you have a whole nother layer of safety now.
But right. So now you have a non-corrosive layer on the inside, so we can use those ones that already are buried in the ground. We don't have to dig new ditches.
Yeah. Now, when you're working here in terms of R&D, how does that process come in? Do you have a private company say, hey, we want to put pipeline from here to here, and we want to use a polymer, what's the best to use? Or are you kind of just independently working on projects to find these new material combinations that are going to be, better or cleaner?
Yeah, so material selection again, what's going to work for the chemicals, for the right chemical resistance, what's going to last the lifetime through accelerated aging. We haven't gotten into full-scale pipe testing here yet, but we're into a lot of material testing.
Okay.
So we are looking at the individual materials in the hydrogen lab and the CO2 lab that we have here. We can measure permeability of hydrogen through a polymer, so I can tell you exactly how much is going to come out over what period of time. We can measure the properties in situ, so we can put it at 3,000 psi H2 at a temperature, and we can watch how the tensile properties change. We've been doing tests on CO2 to see if there's an issue with rapid gas depressurization. So that's where the polymers soak up some of the gases over a period of time, and they saturate. And if there's ever a time when the pressure drops, you get supersaturation within your polymer, which can cause bubble nucleation and growth, which then causes blistering.
Separates.
Yeah, so we're finding the limits for materials for both CO2 and hydrogen for the rapid gas decompression.
Now, when you're talking about the permeability of plastic, I know that's always interesting because all polymers, like you said, are permeable by something at some level, right? Maybe not your bottle of Coke in the fridge, maybe that'll stay good, but ish, right? But when you're talking about hydrogen or, something like that, which is extremely pervasive, um, is there technologies, or are you looking at how to include like perhaps a non-permeable layer? You're talking about mixing materials.
Right.
In my mind as a complete layman is like, well, do your inner liner, then you do a 22 gauge liner of stainless steel, 25 series stainless, and then the reinforcement.
Yeah.
You kind of win everything, but then the costs go up, and then who's going to pay for that, or how do you do it? How do you start working through those issues?
Yeah, so there's some trade-offs there. Some pipe manufacturers are doing these things.
Mm-hmm.
I disagree with your pop in the fridge. There are gases going through there.
Yeah, they're going through there.
PET is the polymer that's used for those bottles, and it's very good for resistance of CO2 going through, so it stays carbonated, but you do get some oxygen through it.
Yeah. That's why it doesn't taste the same when it's been out there for a while.
Yeah. So food packaging, again, it's multi-layer. So you have EVOH in there, you have PET. There's a bunch of layers, and each of them are good at resistance to one gas or another.
Mm-hmm.
So then, I guess getting back to your question about putting a non-permeable layer in there. So some people have put basically aluminum foil.
Okay.
So, very thin aluminum foil in these pipes, and shown that it does work well. It cuts the permeation down to, almost zero.
Mm-hmm.
Some of the issues are if we get gas in between the aluminum and the layer next to it, the polymer layer next to it, then during that decompression,
saturation,
then you really get issues with debonding, disbondment between those layers, and then you could get pipe failure. So you're opening yourself up for other failure modes, the more layers.
Because if it can't permeate out, it's going to just get trapped at that layer.
You get trapped at that interface.
Right.
And then again, it expands if you let the pressure out. So there's always a trade-off, and we're very good here in the lab at looking at how much of an issue is that? How can we mitigate that issue? Can we use something like laser etching of microfeatures to get a better interface between those materials?
Right.
So there's less of a chance.
More of a capillary kind of connection there.
Yeah. Right.
So in terms of, the worldwide aspect of this, there's big pushes towards, green, carbon capture, environmental safety going forward. And when you look at polymers in terms of transport, pipeline, and containment, they seem to knock off a lot of those check marks in terms of safety and use and recyclability and all these things. But the production of the polymers in its initial state is still very carbon intensive, right? So, what's that trade-off, or how's that research looking in terms of not just the utilization, but that material creation?
Sure. So they are petrochemicals almost all the time. These, high-density polyethylenes are coming from the oil industry.
Mm-hmm.
So, yes, it does require drilling and getting crude and cracking it and getting the right polymer out of it.
Yeah.
We as an industry are looking at more bio-based ones.
Yeah.
So I've seen soy-based materials coming up.
I've seen straw stock in South America, polymer-based ones.
Okay.
Yeah.
Yeah, so there's definitely people working on the bio side instead of having a petrochemical as your start, having bio oils as a start.
Mm-hmm.
I think they're making great progress so far. I'm not sure if people are ready to trust them for 50 years.
Yeah.
So that's, again, if you have a 50-year pipeline, we need to do the accelerated aging tests on it to tell you, is it going to keep the properties? Is it going to keep the media, the people, and the land next to it safe?
Yeah, and that's always kind of the trick, is that time, right? When you look at the infrastructure that we have in North America, it's quite old. We're looking at some 70-year-old pipes in the ground, and for the most part, they've held up. And when we look at putting new product in the ground, you'd want it to last at least the same, right? So that must be an obstacle in itself, because plastics, do they hold up? Do the polymers hold up as well as the steels, or is there more engineering that must go in behind it?
I think it's the same amount of engineering, but there's a lot of environmentalists that complain about plastics are forever. They're staying in the environment. They're not degrading. So that's a bad thing when they're pollution. it's a good thing when it's a pipeline. So it's, there's, again, trade-offs everywhere.
Yeah. What are some of the newest things that have come up? Like, what are the really cool things that, in your research or your work here that have been like an aha moment or a light bulb, but it's like, wow, that's cool. This is new. This is good.
Yeah. So I think the polymer to metal joining that we've done recently, even we were surprised how strong it turned out. So what we're doing is we're laser etching the metal side. We're putting micro features in there that basically act like Velcro. So we're putting troughs, we're melting troughs, and as the material melts out of the trough, it melts up the sidewall and then creates little fingers that overhang that trough. That's why I call it Velcro. It's kind of like the hook side of Velcro.
Hook and ladder, yeah.
And then we can take a thermoplastic and we can melt it into those little features, past the hooks, down into the wells, and we can create strengths, shear strengths of 1,500 pounds on a 1 inch by 1 inch sample.
Oh wow!
So we're getting very strong adhesion there.
It's like roughing up the wood before you glue it together, right?
Yeah, but much more kind of
specific and precise. Yeah,
right. And so we've seen very big differences depending on how we do the laser etching on the strength that comes out of that. And we're having a lot of interest from automotive in general and kind of implementing that, some in medical, some in aerospace as well. So getting away from adhesives would make it more environmentally friendly. It would make it a little bit easier to manufacture because you don't have to worry about a shipping cold chain for adhesives and
set time
and curing and open times and green time. Yeah. So getting away from that and being able to bring these together and make that joint in 30 seconds and then it's solidified rather than waiting for it to cure.
Now, how far are we from, as an industry, being able to take some of these advancements and company X buys the machine that produces these type of materials?
So we're working to get there with some of these. So we've shown it on the lab scale and we've shown it on representative parts for a couple different industries. And now it's going to be up to our customers to, put the investment in to get it to the manufacturing. But I think if somebody gets serious about it, in 2 years, we could have something really out there. And, working, being sold.
And have you had to develop new technologies in order to create these new products? Because, some of it sounds like it exists already, like laser etching into plastic. Okay, we get that. But have you had to have those moments where you're like, we don't even have the machine to do the thing that we're thinking about doing?
We have had to do that.
Yeah.
For this particular one, we're using a machine that wasn't made for this. So we really took it outside of its core capability and redid it.
Yeah.
There's another machine that we actually built in the lab that didn't exist for dissimilar polymer welding. So for dissimilar polymer welding, most of the time when you do polymer welding, you're joining the same polymer to itself. Dissimilar, we're talking about, again, like the automotive interior. When we have two materials coming together that look different, that feel different, that are different, how do we get them to stick? So in polymer welding, we need intermolecular diffusion between those parts. So polymer chains from both sides entangle at the interface, and then we cool them down, and now they're stuck together. In order to do that, we have to have similar viscosities, melt viscosities, while we're joining them. So the polymers, when you heat them up, they have different melt viscosities at different temperatures.
Yeah.
We have a rheometer here so we can measure that melt viscosity as a function of temperature. And on this custom piece of equipment that we built here, Dr. Miranda Marcus really was the leader of this. And we can set two different temperatures for the two different materials. So we're not matching temperature, we're matching melt viscosities. And we've seen a huge increase in strength at that interface when we're melting those viscosities.
When you look at a piece of polymer, like let's say you have a 1 by 1 foot square, and you have to have a joining edge, how homogeneous is that polymer from end to end? Are you you're talking about using viscosities versus temperature, and I assume that's because it's going to be slightly different temperatures at different points, and it's not the temperature you're trying to get, you're trying to get that liquefaction to be at that right point for the next one to join in it and be happy. How much does that move or change in the production of a polymer?
So typically not that much, maybe a few degrees here or there.
Yeah.
But the polymer suppliers have gotten very good at making the same product, ton after ton after train car after train car. So typically you get a certification for maybe a melt point or a glass transition temperature from the manufacturer when you buy that next lot of material. So we're not talking about big changes within a single material.
Okay. Yeah.
Just, the difference between
materials.
polypropylene and HDPE.
Mm-hmm. Now, in terms of the technologies that are coming out to help with this production, because this is in a lot of ways going to be the future of a lot of materials, do you see industry getting behind this? Do you see a lot of companies being like, yeah, let's start making the transitions? You talked about automotive, you talked about aerospace, are we talking about household things? Are we talking, how wide or vast is this industry?
Yeah, no, consumer goods as well. We have customers in that area. So really it comes down to, can they be more green if they use this? Can they spend less money on manufacturing? Can they have less materials in their plant? And if the answer is yes to any of those, then they're going to start to jump on these and start to use these technologies. So again, we're in early stages with half a dozen different companies doing these kinds of things, and they're all doing feasibility trials with us now. And that's really our bread and butter here at EWI, is doing those feasibility kind of at the front end
even
of the
worth
project.
it? Yeah.
Is it worth it? And then if it's worth it, then we help them develop it. And if we have to build big machines that go into manufacturing plants, we work with the vendors that build those machines, and then we help optimize the processing windows that give a good part every single time.
Okay, so kind of right from like inception to product rolling out the door.
Yeah, so we're going to be there throughout the whole part, all of it. If needed, we'll go to the manufacturing plant and we'll do kind of that installation process and that the first products coming off of it. And then, after that, we'll be consulting for if something goes wrong in the future, an operator pressed the wrong button.
Yeah.
We can go back and say, oh, this
what
has
happened. Yeah.
Right.
Now, you brought up sustainability and green a couple times, and those are very hot topics for all of industry going forward. And we talked also about how it's kind of a little bit of a catch-22 with sometimes you want these products to last forever for safety, but then you talk about forever products. We don't want microplastics in our water and in the food and so on. How do you balance that need for consumer goods, which when you look at consumer goods, we have very little control on what happens to them after the fact, as opposed to, say, a pipeline or something where it can be very regulated. How do you manage that sustainability?
So I think it's making products with less materials again. So
try to use as minimal as possible.
Right. If we use more thermoplastics and less thermosets. The thermosets are things that cure, things that when you heat them up, they degrade. They're very hard to recycle. Again, airplane skins are made of them now. There's a lot of airplane manufacturers looking toward thermoplastic composites instead of thermoset because they are more recyclable. We can heat them up. We can get the carbon fiber back out of them.
Melt them back down.
We can melt the polymer out and use that again. So I think making it more things out of recyclable plastics. So instead of the adhesives and the epoxies, then we can separate them at end of life and we can use them again. So again, that's easier for the bigger industries where we know what happens to a plane at end of life rather than consumer products. We don't know if somebody's really going to recycle that PET bottle.
The car seats. Yeah.
Those are tougher. It's tough to get a consistent product out of a car seat that's been in your car for a long time and may be partially degraded.
That's right.
So those are a little more difficult to recycle, but it's light, it's easy to move. Plastics still have advantages, to daily life.
Yeah, I don't think we're ever going to get rid of them because, even with the bioplastics, I have been at conferences around the world where that's a big topic. Some countries are investing heavily into bioplastics because it's also part of sustainability because you're taking waste in many cases, and the waste can be turned into usable plastics, right?
Right.
Now, in terms of, other construction materials, do you ever work with like polymers? I've read about polymers in cement, polymers in construction materials to strengthen bricks and other types of materials. Is that something that's also part of like on the radar of what you guys do?
Yeah, definitely. We had a discussion last month with someone that's very interested in putting waste polymer into cement and getting a better product out at the end. So it's a great use for end of life polymer that maybe isn't high enough quality for making another product.
Yeah.
But instead taking, grinding it up or making pellets of it and putting it into cement and making that stronger. So yes, those types of things are also things we're looking at. And again, we're very good at the interfaces, the material science, and the characterization of, is this really making the product better?
Yeah.
Is
or
it
are we just hiding stuff?
Right.
Yeah.
Yeah.
Now, what's one project you're working on right now here at EWI that's really piquing your interest, that's got you excited?
So besides the pipeline one, we talked about that one, I think,
Yeah.
enough. But another one that we're developing, and this goes maybe outside of polymers a little bit, but it's something that we're developing. It's called Leak Sight, and it's a new way to detect leaks in products that need a hermetic seal.
Okay.
So what we did first is we determined what gases we could use to do this, and then the real advantage of it is it changes color at the places that it leaks.
Oh, wow.
So it's a
Okay.
product
Yeah.
that you can either tape on, or you can paint on, or you can spray on, and then you put a challenge gas on the inside that's non-toxic at the levels that we need to put it, the concentrations. And then what happens is if there's a leak anywhere in it, it goes from white to purple.
It'll react. Yeah.
So, and it stays purple. So really, we developed this for electric vehicles. The battery box on an electric vehicle needs to be hermetically sealed. We've been in some plants that we've seen they're dipping it in a huge tank. It's as big as the car, so this is a big piece.
Yeah.
Getting the whole thing wet and then looking for bubbles and then trying to determine where those bubbles were after they pull it out. Where this would be a dry way to do it.
Yeah.
So we could put that tape or the spray on the outside. We can put the challenge gas on the inside. Maybe 30 seconds later, we see purple spots.
So kind of like a dye pen test for steel, but for plastic.
Yeah, it's just for gas, not permeability, but
Yeah.
leaking.
Okay.
If
yeah.
there's anywhere that it is leaking, it will show up purple, and then they can go back and do rework on those spots.
I can see that being so useful even on a maintenance side down the road. Even a post-production of things maybe 10 years down the road being like, well, let's check. Well, oh, yeah, there it is. There's the leak, right?
Right.
Now, can that be used for foods as well and other, like anything hermetically sealed?
Can we use for foods? It is. So the formulation that changes color is actually edible. So we don't have to worry about toxins.
Like nitrogen maybe as a gas. I don't know.
I don't want to say what the gas is. It's part of the
secret spice, the 11 secret spices.
You have to read the patent if you want to do that. But at the concentrations again that we're putting in there, it is underneath OSHA levels for working an 8-hour shift.
Okay, yeah.
So it's very low concentration. It could be used for a lot of things.
That's interesting.
Yeah.
Now, I guess I've never really thought about that. There's the building, there's the usage, there's the welding, the joining, the degradation, but the testing. How do you test plastic?
Yeah.
And that's something, and I'm not talking about in the lab, I'm talking in the field, because with the metal, the steel world where I come from, there's still new technologies coming out for testing all the time. When I started welding, there was no phased array. Now we have, PMI testing right on spot and stuff like that. In the plastics world, the polymers world, is there also a whole industry of testing that kind of advances with it?
Yeah, so our non-destructive evaluation group here is working on that. It's not nearly as far along as the metals world, but we're seeing which techniques work for plastics. So your UT phased array will be able to see voids in the plastic. It'll be able to see that density difference
Okay.
when you put the acoustic wave through it. Other ways that we've looked at are thermography. So flash thermography, where we're heating it up, and then we're seeing differences in thermal conductivity between places where there's voids and places where there's not.
Right.
So we can look for
discontinuities,
discontinuities in parts to say that, there is a void here, there's a crack here in the middle of a part. Those things are good for the field, and we're actually working on inspecting the composite pipelines using those types of techniques as well.
And then if you find a discontinuity, what's the repair? Like, I mean, the welder in me thinks, well, you're going to grind it out and fill it with some liquid plastic and call it a day, or, I'm not sure. Or is it a complete cutout and a new length comes in?
Yeah, it depends on what the product is. But for a pipe, you're typically going to cut it out, and then it's going to take 2 new connectors and a new piece of pipe in between them. You can't really repair those pipes.
Not yet.
So we haven't figured that one out yet. We'll keep thinking about it.
Open root pipe welding, here we come.
Right. Yeah. Now, once you kind of sever the reinforcement layer on those multi-layer pipes, then it's lost its strength. So we need to chop it out, put new connectors in, put a new piece of pipe.
Put a new piece in. What about globally in terms of collaborations? These issues are being tackled by groups, research labs, governments around the world. Does EWI or your team have collaborations with other partners, either here in the Americas or around the world, to kind of work on these problems? Or are you basically just working on the customers that come in the door?
We try to think bigger than the customers that come in the door. So we do watch market trends, and we watch for gaps in technology. I would say we're probably closest to the customers we work with because we're hearing their exact problems.
Right.
They're things that they will tell us that they're never going to put in a report that goes public. So we do learn more faster from our closer clients. But again, we are, reading things that are affecting the world and trying to come up with solutions for those as well. So
try to be a little bit more proactive about what's coming down the pipeline.
But there.
Nice. Yeah. I've been working on that one all week. So
yeah.
Last couple questions. What's something that's really, that you think that EWI is really on the forefront of, in terms of the projects you're working on and what's coming out into the industry are you in the work that you're doing with your team? What are the things that we're going to see in the next few years that are going to be like, wow, that's amazing?
Yeah. I would say more dissimilar materials joining.
Things that normally would have never been figured out.
Right. Without adhesive. So we're also working on laser welding of composites, the thermoplastic composites I mentioned that Aerospace is looking at now. And we've come up with some great ways to do that even if they're glass filled or they're carbon fiber filled, or, they're these high temperature aerospace polymers, we can weld them together with high strength in a short amount of time using some different lasers. So we use a couple different wavelength lasers. 1 micron is used a lot in metals. We use it in polymers for through transmission laser welding, but we need an absorber in one of the polymers to do that, something like carbon black.
Something to take the heat,
The second one that's more up and coming, it's been out there for a less amount of time, but we have one here in-house already, is a 2 micron laser. So it's a longer wavelength, and it partially absorbs into polymers, so we can set the focal length at the interface between those polymers.
Instead of having to hit that back.
Right, and then we can join things that are non-filled, even transparent.
Oh, okay.
So medical really likes it if we can do transparent to transparent with no fillers. So I think these materials, that and the metals to polymers, more and more products need to be composites.
I've been seeing lots of that,
So you can lightweight if you can take part of your car frame and make it a composite, whereas some of it still needs to be aluminum or steel for the strength. So, we're coming up with new ways to join dissimilar materials often here. I think more of those will be implemented into the products you see. They'll be composites rather than a unibody of one material.
And I think that's really, like, if I could if I could think of a theme for the future, it's collaboration. Not just collaboration of industries, collaborations of sciences, but also collaborations of materials. And the previous podcast we did today was great. It was one of the quotes from James from Josh, sorry, was that eventually we're going to need everything. We're going to need a little bit of everything to get ahead, and all these sciences are all going to come together, right? And I think plastics kind of hit a peak in society where it was like, this is just a product that we use to, for Tupperware and for chairs and stuff. And then eventually someone was like, well, I'm sure this can go further, and now we're getting to see how far that product can take us, right?
Yeah, there's more and more engineered plastics, but now joining those engineered plastics to other materials and creating something truly unique
Yeah.
is opening up possibilities for new products.
That's amazing. Well, what's something that you would like the public to know from yourself? As a doctor here, as an engineer, as a researcher, when you talk about, there's always these questions. People don't really understand the world that we live in. If you could say something to somebody, what's something about polymers that you would like to tell them?
Just notice how much we use them every day. How many polymer joints there are in everything that's in your pocket, to your laptop, to your car. Let's not think, let's not muddy the waters of single-use plastics,
Right.
with the things that are durable and that last, that we use every day. So could we reduce single-use plastic? Sure, that would be a great thing and have less waste in the environment. But we need them for airplanes and cars and pipelines. So
yeah, and cell phones and computers and everything.
Exactly. We need all of these products. So
Let's find the best way.
Yeah, don't think just plastics are a waste and pollution in our environment, but instead think of all the good things that they do, and we'll come up with ways to reduce the amount of single-use plastics.
Awesome. That's great advice. And it always takes multiple levels of thinking to get through these issues and obstacles. And like we said, like you said, we're not going to get away from plastics. If anything, we're going to become more reliant on them. So let's find a better way to do it, right?
Exactly.
Awesome. Well, thanks so much for being on the show, and I really appreciated you having here, man.
All right. Thanks for having me. It's been
fun. Yeah, good. And for all the people following along our EWI podcasts here, these are be great. We're going to have about 4 or 5 that we're going to do, and we're going to be learning lots of great topics. So make sure you catch the next one. Please also download and share these amongst your friends. We love having the podcast get out there. So take care, and until the next one, we'll see you there.